Hey everyone, welcome to today's Explainer. Go ahead and find a comfortable spot, take a deep breath, and let's jump right in to explore our topic for today, polyvinyl chloride, the shapeshifter.
Today, we're taking a really calm, focused look at the quiet architecture of our modern world. Now, before we get into the heavy chemistry stuff, I actually want you to just look around the room you're sitting in right now. Like, what invisible materials are literally holding your world together? Maybe glance down at that soft charging cable plugged into your laptop, or look at the sleek, rigid frames around your windows. Think about the soles of the shoes you're wearing. We interact with these everyday objects constantly, right? And we kind of take their silent reliability totally for granted. But what exactly are they made of?
Okay, so let's dive into this by defining our foundation. To really understand PVC, we first need to get what a plastic actually is in engineering terms. Honestly, it's wonderfully simple. Plastics are basically polymers that have this super cool property called plasticity. All that really means is they can be permanently deformed, molded into a specific, desired shape, just by hitting them with some heat and pressure, often with the help of a little catalyst. They are literally materials born to adapt.
So you might be wondering, why do engineers absolutely love them? Why go with plastics over traditional materials like, say, metals or wood? Well, for starters, they have a remarkably low fabrication cost. It's just cheaper to make. But more importantly, they are incredibly resistant to corrosion and really harsh solvents. Like, they aren't going to rust away the second they get left out in the rain. They're also notoriously bad conductors of heat and electricity. I know bad conductor sounds like a negative, but that actually makes them totally perfect for insulation. Plus, surprisingly enough, their stress-strain relationship is actually quite similar to metals. So you get this quiet, safe, and highly functional reliability.
Which brings us to part one of our journey, the origin. A quiet, inert powder.
You see, before it becomes a pipe, or a flexible raincoat, or that laptop cable we just talked about, we need to look at its origin. In its absolute baseline state, PVC is literally just a colorless, chemically inert powder. It just sits there, completely unbothered by the world. It's not inflammable, it has a specific gravity of 1.33, and this super precise melting point of 148 degrees Celsius. And guys, it is incredibly resilient. We're talking resistant to oxygen, carbon dioxide, moisture, even light. It's basically a blank, peaceful canvas just waiting for a purpose.
So, how does that raw, peaceful powder actually come into existence? Okay, take a breath. You absolutely do not need to memorize this chemical equation. I promise, no pop quizzes today. I just want you to take a second and observe the elegant, almost rhythmic chemistry happening. It's just a beautiful sequence showing exactly how a long, complex polymer chain is born from a few really basic ingredients.
Let's break that elegant chemistry down into a super simple three-part journey. First up, we start with acetylene and hydrogen chloride. Simple enough, right? Second, we apply a gentle heat, somewhere between 60 and 80 degrees Celsius, along with a metal oxide catalyst. This really peaceful, perfectly controlled reaction gives us our monomer, which is called vinyl chloride. And then finally, we take that vinyl chloride and heat it up in the presence of benzoyl peroxide or hydrogen peroxide. And through this step, the molecules basically link hands, creating polyvinyl chloride. Just like that, a completely new material is born.
Now, a really crucial point here is that PVC belongs to a very specific family of plastics known as thermoplastics. What does that actually mean for us? Well, it means the material gets nice and soft when you heat it up, and then almost magically, it regains all of its rigidity simply by cooling back down. This curing by cooling thing, it's basically a superpower. It means PVC can be shaped and then reshaped, endlessly adapting to whatever form we need it to take. Moving right along to part two, the unbending. Let's look at rigid PVC in engineering. Let's explore the two incredibly distinct lives this material can lead, starting with its completely unyielding form. When PVC is left alone in its natural, unplasticized state, it becomes what we call rigid PVC. Without adding anything extra to soften it up, it holds on to all those baseline properties we talked about earlier. It stays chemically inert, it stays non-inflammable, and it fiercely holds on to that high softening temperature of 148 degrees Celsius. In this form, the material is tough as nails. It's protective and completely unbending. And because it is so unbending, engineers love to use it to protect us in some seriously heavy-duty ways. I mean, it's used to mold the hard safety helmets that construction workers rely on every single day. It forms the super durable components hidden inside your refrigerator. It's used in tires. And actually, it's the exact material making up the mud guards on a bicycle or a motorcycle. Seriously, next time you're riding your bike across campus on a gross rainy day and that mud guard stops a puddle from splashing all over your backpack, you literally have rigid PVC to thank for that.
But there's a whole other side to this material. Let's look at part 3, the yielding, plasticized PVC.
So we've seen the unbending side, but what if we want to build something completely different? Well, engineers use a little bit of chemical magic known as a plasticizer. Specifically, they take that PVC resin and mix it uniformly with a plasticizer, something like dibutyl phthalate. Adding just this one single ingredient completely flips the script. It literally transforms the material. It takes that rigid, tough-as-nails plastic we were just talking about and turns it into something soft, pliable, and incredibly yielding. It's a total game changer.
Once we have this plasticized PVC, an entirely new world of applications just opens right up. We go from those heavy-duty bike mudguards to flexible raincoats that comfortably shed water. We get soft beach shoes, tablecloths, handbags, curtains, the whole shebang. And critically, because it still remains a really bad conductor of electricity, this yielding version of PVC is what wraps electrical insulators. Yep, those radio, TV, and laptop cables that are quietly and safely charging your devices right now, that's plasticized PVC doing its job.
Honestly, it is truly marvelous to step back and realize that a single colorless base powder can serve two entirely different physical purposes, entirely based on how it's treated. On one side, we have rigid PVC, unbending, fiercely protective, perfect for things like helmets and mudguards. But then on the other side, we have plasticized PVC, yielding, flexible, blended with plasticizers to give us raincoats and soft charging cables. Two vastly different worlds from the exact same starting line.
Which brings us to our final section, Part 4, A Quiet Material World, Finding Balance in Structure.
As we wrap up our time together today, let's take all these cool engineering facts and kind of bring them back to a human perspective. Polyvinyl chloride teaches us something really beautiful, actually. It shows us that you can have a remarkably strong, resilient foundation, but by adding just a little bit of flexibility, just a little bit of yielding to your naturally unbending nature, you can completely change your utility in the world. So next time you plug in your laptop or throw on a raincoat, I really hope you remember the quiet adaptability of PVC. It kind of makes you wonder, doesn't it? What other invisible structures in our lives could maybe benefit from just a little bit of flexibility? Thank you so much for joining me for this explainer. I'll see you next time.